Okay, almost there. Two more. Corollary 440. If T is an operator on a Hilbert space H, then there exists a positive operator Q and a partial isometry W such that T equals QW. Moreover, W and Q are unique if the range of W is equal to the orthogonal complement of the kernel of Q. Now, this proof is going to rely heavily on the one before it, as you can see some great similarities between the two. So first we're going to consider T star, and by 4.39, the theorem that we just proved, there exists a partial isometry and positive operator W such that V, this should be a W, this should be a P, and partial operator P. Vp is equal to T star. Now, because P is self-adjoining, we get that when we take the adjoin of both sides, this gives us PV star T, which is now in the form that we're looking for the problem, where the positive operator comes first and the partial isometry comes second. So what we're going to do now is we're going to say that we're going to let W equal our V star. So that's going to be our partial isometry, W, and Q is going to equal P, giving us the desired result. Now, for uniqueness, we're going to again rely on the theorem before. For uniqueness, so we're going to write up a quick set of equivalences. We know that the kernel of V is equal to the kernel of W star, and by theorem 4.6, this is going to be equal to the range of W orthogonal complement. Now, as well, we get that the kernel of Q double orthogonal complement is equal to the kernel of P. Again, because these are closed subspaces. Kernel of P would be a closed subspace. So from this, what we can now deduce is that if we take the assumption from the first problem that the kernel of P, that they are unique when the kernel of P is equal to the kernel of V, then we get that these two are equivalent. So we get that, so when kernel of V equals kernel of P, we get that range W is equal to kernel Q double orthogonal complement. Now, why is this important? Well, this here, because again the range of W is the orthogonal complement of the kernel of Q is a closed set, we get that this would then imply our desired result, that the range of W is equal to the kernel of Q bar, as desired. But as well, if we take this assumption, if we take this to be our primary assumption, then we need to show that uniqueness still holds. So if we assume it to be unique, we get this, and if we assume this, that the range of W is equal to the kernel of Q closure, this implies that the range of W's orthogonal complement is equal to the double orthogonal complement of the kernel of Q. But this gives us equality of kernel V kernel P equals the kernel of P, which by proposition or theorem 4.39 we get gives us the uniqueness of our V star and our P because the uniqueness of our Q and our W because P and V star are in fact unique.